In this lesson, we will learn normal distribution. Normal distribution is one of the most commonly used distribution in statistical inference. A lot of our later procedures, including confidence interval and hypothesis test, will all rely on this distribution. In some cases, we need to assume the data follows normal distribution, and in some other cases, we do not need to make an assumption about the data, but because of the sample size being large, the test statistic or the statistic to be used for estimating the parameter could behave like a normal approximately. So we need to get familiar with the distribution and use it for our inference. This distribution is a symmetric distribution and centered at 0. And we will try to use it to consider the probability computation and also the quantiles from the distribution. The normal distribution is people often say bell-shaped curve. That actually is referring to the normal distribution. But not all of the bell-shaped curves are normally distributed. In fact, this normal distribution are actually specifically referring to a PDF given by a particular function. You will see it soon. Sometimes the normal distribution is also referred as Gaussian distribution. So both normal or Gaussian distribution are referring to the same distribution. The next slide here shows that some of the normal distributions, the different normals, they could have this different mean or different standard deviation. All of these, even though they look like very different, but they are all in the same family of normal distributions. The red one here has a center of -4. So here, if you look at this red one, it is centered at -4, and the standard deviation is 3. On the other hand, this blue one, if we look at the blue one, it is centered at 0 and a variance of 1. So this is centered at 0. That's blue one. And the purple one is centered at 10. So here, this is the center. 10 is the center, and standard deviation is 0.16. The standard deviation basically determines about how much the possible values will spread out around the center. In these different situations, you can see that the standard deviation of 0.16 would give us majority of the values centered around this mean. And on the other hand, if you look at the red one, it has the most variation and the values are further apart from the mean. Just like I mentioned, not all of the bell-shaped distributions are normal. Here are some examples that are not normal distributions. In fact, for the normal distribution, the probability distribution function has to be given by a formula shown here. This is the normal distribution, and inside of this distribution, what is important is that this part is x minus mu squared. So it's like x is the value, a possible value of the variable, and mu is the mean, the center. And denominator is twice of the sigma squared. Sigma squared is the variance. And here we have a negative. So this is the talking about the x minus mu squared over the 2 sigma squared. If you think about this x minus mu over sigma, this basically, you can think of it as a value z, and this z tells how many standard deviation, away from the mean. So this basically, in the exponential part, is -half of the squared, how many standard deviations away from the mean. And the outside here, we have 1 over square root of 2 pi sigma squared. And this formula is particular for the normal distribution. We could change the mu or sigma for different mu or sigma that would refer to the different normal distribution. When you change only the mu and maintain the sigma to be the same value, then you are basically shifting the location of the distribution. And if you stay the same mu, but for different sigma, then you are changing the spread of the distribution. Okay. On this plot here, you see some other distributions. They are not normal distribution, even though they are also symmetric, centered around 0. Out of this plot, the only one that is normally distributed is the one with the black colored curve. That's the standard normal distribution with mean 0, variance of 1. The blue colored is the logistic distribution. For this distribution, you can see that we have a much more probability on the center part compared to the standard normal. In the very center, close to the 0, like this part, there's more for the logistic distribution, this part. But when we look at the part between the -2 to this value, so this part, the normal distribution would have higher probability compared to the logistic distribution. On the other distributions listed here, they are, oh, I'm sorry. Just now I was listing just one of the logistic distribution, okay? And these logistic distributions, they also have parameters. When we change different parameters, we will have other probability assignments. If you look at these other blue colored, here are some of these that's logistic distribution that has probability on the outside, so more on the tail side. That's the logistic distribution. In general, logistic distribution would have more of the probability on the tail side compared to the normal distribution. The red colored distribution on the plot, these red colored, they are the t distribution. T distribution compared to the normal 0, 1, the standard normal. In this case, you do not see too much of a difference, but still on the tail side over here, there are some more probabilities for the t distribution. In this plot, because of the logistic, this one that's tall, so the overall vertical axis was being shrunk, so that it's hard to see the t distribution, how much it deviated from the normal. Later on in chapter 8, you will see when more of the t distributions are plotted, you will see the difference between the t and normal. So in general, comparing normal distribution with mean 0, variance 1 to the t distribution also has more probability on the tail side. The mean and standard deviation, as we have already mentioned, the mean is given by the mu and standard deviation is the sigma. And once we give the mu and the sigma, the entire normal distribution is completely determined, because the whole PDF function only depends on these two parameters, and the rest of that is simply just the variable's value. Okay, so this kind of characteristic, given the mean and standard deviation, it determines the distribution. Such characteristic is not always the case for other distributions. In some other distributions, additional parameters are inside of the PDF function. Okay, so for the normal distribution, if we give the mean, give the standard deviation, and we know the entire distribution, beyond that, if we're given the mean and the standard deviation, we are also able to compute all of the quantiles and also probabilities related to it. When we have the mean being 0, standard deviation being 1, in that case, this normal distribution, a random variable from that distribution often is using the z to write it. So z often is used to denote for the standard normal distribution. Standard normal refers to the mean being 0, standard deviation is equal to 1. The notation for this z follows the standard normal distribution. We can write it like this. The z follows the normal with mean 0 and variance of 1. So this part gives the mean, and this one gives the variance in this notation for the normal distribution. Okay. Oh, in this notation, I have a z and then a tilde. This tilde just to mean that the distribution follows something. Okay, follows that distribution. Probability for the normal distribution, random variable from the normal distribution, we already know the probability is given by the area under the curve between two numbers. In the normal distribution, the center is mu. If we try to consider the to A and B, again, this part between A and B gives the probability. But in the normal distribution, there is something special. What's special is consider the entire curve. We will know pretty much clearly that the smallest possible value that we observe will be around 3 standard deviation below the mean. So here is mu minus 3 standard deviation. And this the larger side on the upper end, the large value would be around the mu plus 3 standard deviation. And so you know mu and 3 standard deviation is that much, therefore you can tell about where's the 1 standard deviation above the mean and 2 standard deviations above the mean. So that's the special case for this normal distribution. 3 standard deviations below and above the mean, that already contains the majority of the possible values. Not only majority, is nearly all of that. So here gives the PDF again and also the area under the curve, which is the probability. If we consider the K to be 2/3, so 2/3 standard deviation below and above the mean, that give us about 50% in the middle. And if we consider 1 standard deviation, so here, if you look at it, this mu minus sigma, and here's the mu plus sigma. 1 standard deviation, here's the mean. Below the mean, this part distance is a standard deviation. So 1 standard deviation below the mean and 1 standard deviation above the mean, this part is also the sigma. This entire range would capture 68.3% of the probability. Okay. And then the next plot here, the lower left, the one is 2 standard deviation below and 2 standard deviation above the mean. Now, if we look at the in between, the probability is 95.4. So with the normal distribution, the standard deviation give us important information. 2 standard deviation below and above the mean would already give us 95.4% of the data, captures that much. Now, if the last panel on the lower right, if you see between 3 standard deviation below and above the mean, the entire area is 99.7%. So basically, almost all the probability is within 3 standard deviations around the mean. What's shown on this slide, these 4 pictures, they are basically the empirical rule. The empirical rule basically says that how many standard deviation away from the center that area gives what's the probability. So here is the summary of that empirical rule. If we consider the 2/3 standard deviation below and above the mean, then we have 50% of the values in there. If we consider 1 standard deviation below and above the mean, then 68.3% of the data is in there. And 2 standard deviation below and above the mean is 95.4%. And if we consider 3 standard deviation below and above the mean, it's 99.7%. In all these cases, the mean is the center. You simply go to the left or to the right by a certain number of standard deviations. So this is the empirical rule. So we already know the 95.4% of the values are between 2 standard deviations around the mean. In that case, if we try to think about this value of mean minus 2 standard deviation, so in the middle, we have I'm drawing it again here. So in the middle is 95.4%. because the probability density function is symmetric around the 0, the center. Therefore, the left tail and the right tail probability, that's identical. They are the same. And what's in each tail is half of 1 minus the 0.954, half of that. And half of this one is equals to 2.3%, so 0.23. Therefore, 0.023, okay. So one side of that, this is 0.023, 2.3% is on each tail. Therefore, when we consider this value that's on the lower side, this value on the lower side, this is really the 2.3 percentile of the distribution of the variable. And similarly, on the upper end, you can call it upper 2.3 quantile, or call it 1 minus 2.023, which is the 97.7 percentile. Okay, 97.7 percentile. Similarly, we know that with one standard deviation below and above the mean, that captures 68.3% of the value. So in that case, how much is in each tail? For this case, the middle give us 68.3, and then each side here, this part would be half of the 1 minus 0.683 divided by 2. So that's the amount. That's about 16%. So that is 16%. And then we would know that the value around here, this is the 16th percentile. I can write 16th percentile. And similarly, the other side would be 84th percentile. You can also say it's upper 16th percentile. The next one is consider the mean plus minus 2/3 standard deviation. In that case, we know the middle is the 50% from the empirical rule. And from there, if middle is 50%, and then what we have on the outside, okay, so that's the outside. The middle is 50%, so outside on each side, that's about the 25%. And this one would be the first quartile, the lower quartile, or 25th percentile. Okay, and this one on the other side, this mean plus 2/3 standard deviation, this is the third quartile, or call it the upper quartile. Okay, this is just using the empirical rule to tell what are those percentiles. Here's an example. The example is talking about the amount of pollutant in a randomly selected automobile in Houston, Texas. Let's say, suppose the amount can be modeled by normal distribution with mean 70 parts per million and standard deviation of 10 parts per million. That X denotes the emission level of a randomly selected vehicle. What's the probability that X is less than 60? For this question, X less than 60, we can think about it as 60, how big is the 60 compared to the mean? How many standard deviation away is 60 away from the mean? So center is 70. We have the 70 as the center, and standard deviation sigma is equal to 10. And we know above, this would be the total of 3 standard deviation. So the maximum here, 70 plus 3 times the standard deviation, this is about 100. And this side minus the 30 would be around 40. Okay, and the question of 60 is just one standard deviation below the mean. So earlier we already know from previous slide, if it's one standard deviation below the mean, then it's the 16th percentile. And for the 90 is 2 standard deviation above the mean. For the 2 standard deviation above the mean, earlier we already know that it's the 97.7 percentile. So that was this one, the 97.7 percentile here, when we have a 2 standard deviation above the mean. Okay, so this kind of a computation relies on our familiarity with the empirical rule. It's kind of inconvenient, but later on we'll learn how to do the computation of this probability with a much easier R code to do so. So this next little part is, what's the probability that X is between 60 and 90? For this question, we can just use the probability in between to help us. We have a 97.7, that's for the probability. Okay, so I'm going to write it write it like this: X less equal to 90, this is the 0.977, and we also know the probability of less than 60 is 0.16 roughly, and in between would be the difference between these two numbers. So 0.977 minus 0.16, that gives us the probability of between 60 and 90. Okay. How could we tell whether the data comes from the normal distribution or not? In the past previous lesson, we learned that there's the histogram or using the box plot, but unfortunately, either the histogram or box plot can only show the data being symmetric or not symmetric, but we cannot tell whether the data are actually having the normal distribution or from other symmetric bell-shaped distributions such as the T or logistic. So instead of histogram or box plot, when we try to assess if data comes from normal distribution or not, we try to use this normal quantile plot. Here is an example of the normal quantile plot. The data is the number of ticks on grazing cattle. So what do we do in the normal quantile plot is to consider the quantiles or percentiles from the data, observe the data, and we also look at the same percentiles from the normal distribution. In the normal distribution, we do not have to worry about what's the mean, what's the standard deviation. Instead, just consider standard normal distribution. That's in the horizontal axis. And in the vertical axis, we put the quantiles from the data. So how do we compute those? Those are called sample quantiles. We first order the data from the smallest to largest. Let's denote the smallest observation as Y with the subscript parenthesis 1 that represent the smallest observation, and Y with subscript parenthesis 2 that represent the second smallest observation, and so on. Once we order these values, we have a total n of them. Each one represent around 1 over n, that much in terms of between the first and the second. That distance roughly is about 1 over nth, that much of the, in terms of separation. And this 1/10 basically is about the what proportion of those. So roughly, the smallest observation, we treat it as the I minus 0.5 percentile. So like smallest observation is 0.5 divided by n that percentile. So imagine if n is 100, then the first one would be this 1 minus 0.5 divided by 100. So it's 0.5 divided by 100. So we give 0.5 percentile. Why don't we treat it as first percentile? Because the Y1, even though it's smallest from the data, is not necessarily the smallest out of the entire population. Generally, we do not really observe those that are even smaller. So we here put this slight little adjustment 0.5 on each of those computation of the percentages. So the smallest is this 1 minus 0.5 divided by nth percentile. Second smallest is the 2 minus 0.5 divided by nth percentile. Okay, so if n is 100, then the second smallest is 1.5 percentile. For the third value is 2.5 percentile, and so on. So these are the percentiles. In the horizontal axis, this side, what do we put for this value? This would be the 0.5 divided by nth percentile, percentile from the in the x-axis. So x-axis, what do we put? We'll use the 0.5 divided by nth percentile from the normal, the standard normal distribution. So the normal with mean 0 and variance 1. And similarly, the next point would be the point, it's 1.5 divided by nth percentile. And keep going, we have all of them aligned. This will give us the plot. If we see that all the points seems to be aligned along the, they seem to follow a straight line pattern. In that case, we would believe the normal distribution is suitable. The reason that we can use this to make the judgment is because earlier, as you have already seen, for the normal distribution, what is important is simply how many standard deviations away from the center. So how many standard deviations away, the sigma and the mu. In this plot, in the horizontal axis, with what we are having is just the z value. And the sample quantile, if you think about this one has a straight line, then the straight line would have a slope and also the intercept. And the slope is simply the sigma inverse, and the intercept is simply the negative mu over the sigma. That's because when we consider the normal, we would have x minus mu over sigma equals z. So x here, if the x, if the sample on the vertical axis is the sample quantiles, these sample quantiles come from normal distribution. In that case, they will be centered at that mu, even though we don't have it yet. And it has standard deviation in the denominator. But by looking at the slope, you see here the 1x over sigma, we know the slope is 1 over sigma. So that slope of the line gives us the inverse of the standard deviation. But anyway, this slope and intercept, that's not important. What's important is that whether these points seems to be on the straight line. If they look reasonably following the straight line, then the normal distribution is suitable. Okay, so this slide just explains what is on the normal quantile plot. Normal quantile plot is also referred as normal QQ plot. So this vertical axis are those sorted scores. And then in the previous slide here, we also have some of these scores that seems to have identical value, like these are all having the same vertical value, right? That means that in the observed data, some of the catalogs had the same number of ticks. So basically, identical values are observed for multiple observations. So in the vertical axis, we basically give those sorted values. And then in the horizontal axis, what we're thinking is that these percentiles from the sample, they are estimating the population percentiles if the data is from normal distribution. Therefore, we have the horizontal axis to plot the standard normal distribution, and therefore, if the data is from normal, then we can use the relationship between the x with the z to tell that the data is normally distributed. Okay. So how to use this QQ plot? The thing that we care most is not really what is the slope, what is the intercept. Instead, what's really important is whether the points seems to significantly deviate from the straight line, particularly on the tail side. If the points do not deviate from the straight line, then we believe the variable or the distribution is approximately normally distributed. If the data are not normal, distribution is not normal. For example, they might have a skewed data. If you see skewed data, in that case, the observed quantile in that skewed direction, sample quantiles will be larger than the observed quantiles. So it will be like this. This side is the sample quantile, that is the observed quantile. Here's a line, and the sample quantiles would be larger than the observed compared to the other part. In that case, this is indicating the skewness part. That's the right skewness. The right skewness. And if we have data that are left skewed, that means there are some very small values. And for the very small values, we would also have the quantiles from the sample being smaller than the quantiles from the normal. So in the left skewness, you're going to observe data like this. And even though the rest might be okay. So this is the left skewness. This is the theoretical one, theoretical, lower than the line. So this part, the sample quantiles are here. That's lower. So this is the left skewness. Okay. For outliers, if there are outliers, that means that the data observed larger values than the normal distribution. In the outliers case, it will also end up being too high or too low. So if you have outliers, you can imagine that the data are on the top and compared to the normal. Also here, you also have some data on the bottom. So these, I have too many outliers, maybe just one, a couple of them. Okay, that's the case if we have outliers. If we have multiple of the modality, say you have different mixtures in the data, in that case that you could end up seeing the normal quantile plot look like zigzagging or snaking. Let's see, you will see example soon. This is an example about the case that we have a bimodal. From the histogram, you can see this part seems to be one of the population, and this part is another population, but the two of those data, observed data, were combined together. This happens quite often when people do not really know that the data behave differently. Like, for example, measurements for male and female, or measurements for the younger population versus the older population, and so on. So when we do not know that data really should have different populations, we might collect the data and thought they were the same population. And when the combined data would look like this. In terms of the normal quantile plot, you will see part of that, this is from one population, and the other part seems to be from another population. But when you put them together, you see this kind of snaking. And this one is for the skewed data. We see the long stretch to the right-hand side. This is the right skewness, right skewed, the data. And this is the higher part in the sample quantile. So sample quantile is larger. So this is larger than the ones on the straight line. Then those on the line. Okay, so this is the right skewness. And for the left skewness, oh, I did not have it, but it's similar, but it's on lower on the other side. And here is the logistic one. The logistic has heavy tailed distribution. From histogram, we cannot really tell because it's just symmetric. But when we look at the normal quantile plot, you will see some of these points are in the sample quantile are higher than the line. And similarly, on the lower side, the sample quantiles will be lower than the line. So in these two cases, they are the kind that the data are heavy-tailed. So for heavy-tailed, you will see these points above the line or below the line on the other side. And this one is for uniform distribution. In the uniform distribution, the data, if you plot the probability density function, you would expect that between the lowest number and highest number. In this example, the uniform is from 0 to 100. And you're supposed to have this probability density function to be evenly everywhere. So, but unfortunately, observed real data do not have exactly, will not give us like the data follow exactly this kind of PDF. Instead, if you try to plot a histogram, like this is what's shown. You see some part of that doesn't appear to look like a horizontal line. But anyway, this is how the uniform data look like. When if you take data from, if you take a random sample from uniform again, you might have a different shaped histogram. This is the variability inside of the sample, okay? And if we plot the normal quantile plot, the normal, because all of the data are focused between 0 to 100, there's no data outside of that. So because of no data outside, when we compare to the standard normal, in terms of standard normal, this line would indicate, suppose we use that mean and standard deviation for the normal, then what will happen is that the sample quantile, if you look at the values in the sample quantile, they're lower than the line. This is the light tail in terms of the observed data. Similarly, on this side, the observed value in the sample quantile, they would be larger than those on the line. So this indicates that the data are light-tailed. So basically, for light-tailed, you will see the normal quantile plot to be S-shaped. This S-shaped is for the light tail. And instead, this is heavy-tailed, like the previous slide, heavy-tailed. So that's about the quantile plot. And we already mentioned that the computation of x minus b divided by sigma, that actually connects to something. In fact, this is called a standardization. The standardization, what we did earlier is this x minus the mean divided by sigma. This is a standardized x. So-called standardized simply just minus the mean divided by standard deviation. This standardized will create if x is normally distributed, what will happen is that after we standardize, it will become the standard normal. And what this thing provides is that it's how many standard deviations is x away from the mean. This how many standard deviation plays an important role in the sense that if we simply know the value of x and without comparing it with the mean and standard deviation, we don't really have an idea about probability. But if we know how many standard deviation, we can have a very good judgment about the probability. Okay, so like in terms of 38, for example, is 38 is going to be a large number or not small number. This is in terms of the number of ticks on grazing cattle. 38, is it like is it somewhere on the large side or smaller side? We don't really have an idea. So instead, once we computed, we try to think of it, use 38 minus mean divided by standard deviation, then we'll have a good idea because of the empirical rule. So let's see. The standardization involves the centering by subtracting the mean, here subtracting the mean, and then divided by a standard deviation is scaling, and if we put them together is the standardizing. Okay, and once we did the standardization, then this z would represent how many standard deviations is x away from the mean. What is the good part is that after we do this standardization, if x has normal distribution, then the standardizing does not change the distribution. The z would also follow normal distribution, only the mean and the standard deviation would change. So here's the good part. This is referred as the z-score, and what we have is if this z is positive, then that means that the x is z standard deviations above the mean. And if z is negative, then it's a z standard deviation below the mean. In the text example, if we observe 38 and the mean is 40, standard deviation is 5, then when we compute this z-score, it's 38 minus 40, and that divided by 5 will give us negative 0.4. Then we know that this 38 is around 0.4 standard deviation below the mean. You know, earlier we already considered like 2/3 standard deviation below the mean or above the mean, and this one is only 0.4 standard deviation below the mean. So that's something not very rare, and it's I mean the probability can easily quantified with just negative 0.4 alone. Okay, this z-score itself is also a random variable. If x takes different value, our z will also take a different value. We do not have to worry about mu and z because those are fixed population parameters. Those are determined by the population. So consider them as fixed values. But the x, when you conduct experiment once, you will have x value being one value. But if you run the experiment another time, you might have x being a different value. The corresponding computed z-score would change with the collected x value. Okay, so the z-score here can be thought of basically the change in the unit. It's a change in the, so what is computed afterward becomes the how many standard deviations above the mean. Okay, so this z-score, if we try to look at the mean of it, the mean of the z-score, this is a linear function, and in the earlier lecture we have already learned for the mean of a linear function, it becomes the linear function of the mean. So it's the e of x minus mu divided by the sigma. And the e of x, the expected value of x, is equal to mu. Therefore, this is the 0. And the variance of z, linear functions variance, we are going to have still linear function, but the parameter in front of the scale parameter will be squared. So the sigma squared, the variance of x, and this mu constant does not change the variance, so that becomes 1 because variance of x is also sigma squared. So the standardization will convert the variable, make the variable having variance of 1, mean of 0. So that's the mean and variance. The next thing is suppose we have the variable x and we also have some sort of desired transform, turn the x to y, and the y is a plus bx. This kind of transformation, if you try to convert x to z-score and you convert y to z-score, you will find that both of them, depending on the b, if b is positive, then x and y have the same z-score. But on the other hand, if b is negative, the z-score converted will have negative sign. Why is it like that? Say x converted to z-score, we use x minus the mean. So let's see, if for x, the z of x, okay, is equal to the x minus mean and divided by the sigma x, mu x. Similarly, when we do the conversion for the y, we would use the y minus the mean of the y divided by standard deviation of y. And what is standard deviation of y? Sigma y, because it's b times x, therefore it's the b absolute value times the standard deviation of x. Remember, in the linear function, this standard, when we calculate variance, b will be squared. And while after we take square root, it will get b absolute value. Okay, so that's the standard deviation of y. So because of that, when we put this y minus e of y, what is the e of y? Expected value of y is the a plus b times the expected value of x. So it's the a plus b mu x. So once we put in this y, which is a plus bx, and also the e of expected value of the y, so minus the a plus the b mu, and then we divide it by this b absolute value and the standard deviation of the x, you will find the ratio simply becomes the b over the absolute value of b. Therefore, it's going to be either positive 1 or, I'm sorry, we still have the a and a will cancel out. So this times the zx, because we have b times the x minus mu divided by the sigma x. So we have this, so basically the sine of b times the z of x. So the z-score for the y and the z-score of x, the only possible difference would be the sign in the b. Okay. As long as the b is positive, then the y and x would have the same z-score. This kind, for example, the x could be Celsius and y could be Fahrenheit. If you convert the Celsius to z-score and you convert the size, so originally you have data collected in Celsius, like in international, in many other countries, they use Celsius. And the data have been converted to z-score. And after the data came to US, the people here, they want to use Fahrenheit. Then the z-score with the Fahrenheit will be identical to those z-score using the Celsius, because this b is the 9 over 5, so it's a positive value does not change the z-score. For the z-score versus the original x, the good part is if x has normal distribution with mean of mu, standard deviation of sigma, then the z-score would also have normal distribution. So the z here follows normal distribution with mean 0, variance of 1. And this part is equivalent in the sense that if x is normal, then the z is normal. If z is normal, then x is normal. The two are, you can go from both directions. And if the variable is normal, the z-score is normal. But on the other hand, if the variable is not normal, the z-score will also not be normal. So we already learned the empirical rule earlier in terms of number standard deviations. Now we can see basically that's just talking about the z-score. About 50% of the z-scores are between negative 2/3 and positive 2/3. And 68.3% of the z-scores are between negative 1 to positive 1, and 95.4% of z-scores are between negative 2 to positive 2. 99.7% of the z-scores is between negative 3 to positive 3. All these rely on that the variable itself has normal distribution. If a variable does not have normal distribution, then these will not work. The quantiles beyond those from the empirical rule, then we could actually compute it with R. We do not really want to use this kind of whatever percentage. I mean, or this kind of Z-score to compute. It actually in the textbook, it's basically relying on the Z-score and ask to use a table to find it. The table here, this is a very old way of doing that. I'm going to skip that. So instead, we're going to learn it with a new way. This new way is to use R to compute the probability. And suppose if you have the Z-score, or in other words, what you have is the Z that follows normal distribution with mean 0, variance of 1. And then what you want is what's the probability of this variable less equal to a value. This value is given by the little z. And this probability, this is talking about the proportion of the z-scores that's below the little z. And this probability can be simply computed in R simply by the p-norm with the z here. You simply just after you open R, type p-norm parentheses. For example, p-norm with parentheses, you put 1.96. That'll give you the probability of 0.975. Similarly, if you put p-norm 1.645, you're going to get 0.95. Okay, so that's the proportion of the z-scores below the z. And for the proportion of z-scores above the z, you use 1 minus here. The 1 minus the p-norm of z. Or otherwise you use p-norm of z with lower equals false. I prefer to use this one. If you are familiar with using one, stick with that same way of doing it. Okay. So proportion of z-scores between A and B, the two numbers, simply use the p-norm of B minus p-norm of A. Then that will give us those probabilities. How to find the proportion of z-scores below negative z and above z? You just do it with the same way. After finished all these slides, I'm going to show with the R. Okay, so right now I will just continue. For example, proportion of z-scores below. So proportion of scores, z-scores below negative z, negative little z. You can compute it as the p-norm with negative z. And above, for this one, you use 1 minus p-norm with the little z. And these two, in fact, after you finish computation, you'll find that they are identical. That's because the z and the negative z, these two are, so this is negative z, here's the z, and this is the probability is symmetric on both tails. Therefore, below here and above there, that's identical probability. For other normal distributions, like the mean is mu and the standard deviation is sigma, but in our code, it's inconvenient for me to write the mu or sigma. I'm just going to spell the mu as mu, and the standard deviation sigma, I will just write it as s. So proportion of x values below the b, that can be computed in R with the p-norm b here. So that's the command. You copy this part. For example, p-norm give the probability of I wanted the probability of x, say x follows normal with mean of mu equals 10 and sigma squared equals 4. In that case, when I wanted the probability of x less than the 12, simply can be computed in R with the p-norm. I'll put the 12 there, and I'm going to put the mean 10 there, and the standard deviation is 2. Okay, this part, this is the sigma. Okay, So that gives us the probability of less equal to a number. And for probability of greater equal to a number, you simply use 1 minus the p-norm. Like the probability of x greater than 10 in that example, I would just do p-norm, 1 minus p-norm, and I'll put in the 10 here. This, instead of 10, let me use a different number so you don't confuse that 10 with the mean. Instead, 11. So x greater than 11, I'll put 11 there, and then the mean is still the 10, and the standard deviation is the 2. So that will give us the probability. For the proportion of values in between two numbers, we use the p-norm of the big number minus p-norm of the smaller number. Okay. So here's an example. The amount of pollutant in a randomly selected car in the Houston. We had this example earlier. The mean is 70, standard deviation is 13. And what's the probability that a randomly selected vehicle will have emission level less than 60? So for this one, less than 60, we just need to write this p-norm with the 60 here. And this part is the mean. And the next one here is the standard deviation, sigma. Okay. And submit this command in R will give us the probability. And for part B, what's the answer to that one is 0.22. The next one, what is the probability that a randomly selected vehicle will have emission levels greater than 90? Greater, we use 1 minus the p-norm and put 90 there, and the mean 70, standard deviation 13 in it. That gives us probability like 0.06. For part C, what's the probability that a randomly selected vehicle will have emission level between 60 and 90? We use the p-norm for 90 minus the p-norm with 60. And in both, we need to provide the mean 70 and standard deviation 13. So that will give us the probability 0.717. So as you see, using R will make this computation of the probability easy as long as we remember that in the computation, p-norm give us the CDF. So p-norm is the CDF, probability to the left of that value. And what's provided in the second one here is the standard deviation of the normal distribution. So that's about the probability. The next thing is to find the quantiles of the normal distribution. We'll also use R to find the quantiles. If the distribution is normal with a mean of mu and the standard deviation given by S, then the P's percentile or quantile of normal distribution simply can be obtained with this Q norm and P and the mu and S in it. For example, 90th percentile, this one, this is whatever the mean you feed is the mean of the distribution, S is the standard deviation. For example, 90th percentile of normal distribution with mean 42, standard deviation 3, this can be computed with the Q norm 0.9 and 42 and the standard deviation 3 there, which give us 45.84 here. So this basically means that 90% of the values are below 45.85 for this distribution. 10th percentile of the same distribution, we simply put the 0.1 here. And the next one is 95th percentile of z-score. Z-score means the normal 0,1 distribution. And so in this case, you use the Q norm 0.95. You can provide the 0 and then comma 1. But if you do not provide the mean and standard deviation, it has a default of mean 0 and variance of 1. This example, PSAT exam for high school students, the scores are centered at 500, standard deviation of 100. These scores are close to being normally distributed. Semi-finalists and the finalists of National Merit Scholarship Program are the students who have PSAT scores in the top 3% and 1% respectively. What is the minimum score required to be a semi-finalist? So what do we call this value? So semi-finalist refers to those that the separated top 3% with those below. Therefore, this is the 97th percentile. And this one finalist, on the other hand, is the 99th percentile. We simply just need to find the corresponding percentiles from the distribution. So for the 97th percentile, we use the Q norm 0.97 and the mean and the standard deviation. And for the 99th percentile, we put 0.99 and the mean and standard deviation. So like 732.63, that's the cutoff to determine whether a score is in the finalist or not. Compute the probability of quantiles for multiple values can be done directly in one command. In the previous couple of slides, I have always computing just one probability or one percentiles at a time. These can all be done with the multiple of the input. For example, if we want the 90th, 95th, and 97.5 percentile, we can just directly use the Q norm with these three proportions together. The three proportions need to be separated with comma inside of this C. So this is a vector you provided to the Q norm that will give us the computation for all three quantiles, percentiles. Similarly, the probabilities can also be computed this way. For example, what's the proportion of vehicles having emission below 60, below 70, below 80, or below 90? So in this case, what we want is to compute is the probability of less than 60, less than 70, and the probability of less than 80, and probability of less than 90. All of these are of the same format. So because all of them are less than something, so we can just put all these 60, 70, 80, 90 together in a vector like this one. And then afterward, we feed the vector to the p-norm command and specify the mean and standard deviation that will give us all the probability done in one command. The next one, we want the 90th, 95th, 97th percentile of the emission level. For all these percentiles, we again put all these proportion in one variable, call it Q, and then we do the Q norm with that vector, and then they will give us all of these percentiles at the same time. So that is to get the percentiles. Here, the next two slides, they are just some examples. I'm going to skip them. Okay, so that summarizes what we learned about the normal distribution. In the normal distribution, what is important is to recognize that the distribution is symmetric, bell-shaped, but not all bell-shaped distributions are normal. Instead, the normal distribution is totally determined by the mean and standard deviation. They follow specific formulas. The regular normal distribution and the standardized normal, the standardized variable. So x follows normal with mean mu, standard deviation sigma. Then x minus mu over sigma is called a z-score. The z-score would follow normal distribution with mean 0, variance of 1. So that is the standard normal. And the computation of the normal probabilities can be done by the p-norm. P-norm is the probability to the left of the value. 1 minus p-norm is the probability to the right of the value. And the quantiles or percentiles from normal distribution can be obtained with the q-norm. These probabilities or the quantiles, percentiles will be used frequently later on when we try to consider confidence interval or doing hypothesis test regarding a population parameter. So that's all for this lesson.